All right. So, Jason, one of the PQC Contest 3 finalists that moved on to Contest 4 that never got eliminated, that basically got held in the wings as kind of your plan C or plan D fallback, is Classic McEliece.
Yes, sir. So we've done this before, previous episodes where I tried my very best to take an unbelievably complicated subject, such as, the shortest vector problem of lattice mathematics.
Very mathy kind of conversations.
And ultimately, Tim, what we're trying to do is, you can explain the basis of RSA, why it's hard for a ones and zero computer to solve it.
Yep.
It's due to the difficulty of solving for large prime numbers. Yep. Boom. And everybody just knows that.
Yep.
And even if you don't know number theory, you pretty much understand what's going on. Great. ECC, a little different. It's geometric. Okay. Classic McEliece. Tim, the last time we did this, we talked about code-based cryptography. Code-based post-quantum, quantum-resistant cryptography.
Right. Yep.
And code-based was interesting in that I told you that you had this, think of like static white noise as being the public key. Mm-hmm. And the ability to pick signal out of it was the private key. Mm-hmm. Classic McEliece is kind of similar in its intent, and it kind of rhymes in this. The one thing that most people know about Classic McEliece, if they've been following the NIST thing at all, or if you know anything about the mathematics, is it is well known for having a gigantic public key.
Yeah.
Well, let me explain why.
Okay. That's interesting.
Because you remember how in code-based cryptography, the public key is essentially the gigantic amount of static that's available to the public.
Yeah.
You can hand it to an adversary and go, try to pick out the private key out of that.
Yeah, right.
Right? Or try to pick out the signal out of that.
Yeah.
You'd have to have the code book,
Right.
which is the private key.
Yeah. It's the haystack.
It's the haystack. Well, in Classic McEliece, there's a haystack. And that is the gigantic public key, which is inside. Basically, think of it like a gigantic dictionary with very carefully edited errors.
Okay.
And it's the catching of those errors that is not periodic, meaning a quantum computer has no advantage in that kind of haystack. And that's why a lot of post-quantum algorithms, Tim, are haystack-based.
Okay.
It's because
Got it.
you can't use quantum Fourier transform, which is what a cryptographically, capable quantum computer will actually be able to do, is just be able to look at periodicity and patterns and go, wow, I just solved that fast, solving for large prime numbers. If you use a haystack mechanism, remember, lattice, that shortest vector problem with that twisted telephone poles on the football fields analogy that I gave you. And code-based, which was the static electricity that had some signal in it that you had to figure out. Classic McEliece is about errors inside of a gigantic dictionary. The dictionary is the public key.
Right.
And that's why you have
So it's huge.
1 megabyte, public keys with Classic McEliece. It's by definition how it works. And so the encryption, really works by adding the typos into the dictionary. And so I'm going to throw another analogy at you because this is the way that more classically trained people talk about this. It's syndrome-based think of it kind of like a magic spell checker.
Okay.
Where the typos are thought of, like, if you use a medical analogy, it's like, Tim, your body's very, very complicated, but your specific set of symptoms define the syndrome. Well, a specific set of typos in the dictionary is Classic McEliece. It's essentially the definition of the syndrome is essentially the private key.
Okay.
Because if I knew your syndrome ahead of time, I could cure your symptoms, and therefore I solve the problem. I decrypt. And so therefore, correcting all the typos in the dictionary is quickly done when you know where the typos are ahead of time.
Right.
In other words, the symptoms of the syndrome in the syndrome list, knowing where all the problems in the body are. And I think that that's probably a vast oversimplification. There's I know for a fact a lot of people who would throw stones at me for leaving it there, Tim. But I'm hoping that now in this third iteration, you're starting to see the pattern of, and I love the word you used, haystacks are hard for quantum.
Mm. Right. And so as we're exploring future PQC initiatives, because we're not done with that you could imagine more haystack style approaches.
And that also explains, Tim, the size of the signatures, the size of the public keys, because the bigger the haystack.
Yeah.
I mean, if your haystack ain't big enough, any computer can solve it.
Right.
Never mind a quantum computer. Right. It's just that quantum computers have no advantage over a digital computer. And that's why haystacks are often used for PQC algorithms. So we're now at that point where, that's the reason I chose Classic McEliece, because it kind of rhymed with the last one we did. And yes, I know the math is different. Part of what's also different, Tim, is Classic McEliece is phenomenal because it doesn't leak anything. Okay. And in fact, we got a whole episode about, you remember how you and I talked about
no side channel attacks,
or a whole other topic we're going to do later today, side oracle attacks.
Oh, interesting.
And so therefore, whereas, yes, Classic McEliece kind of rhymes as a haystack analogy to code-based HQC, for example, the problem with HQC is it could potentially be vulnerable to side oracle attacks, where Classic McEliece is so straightforward, the larger public key, that it doesn't leak information as into the side oracle.
Right.
There you go.
All right. Thank you, Jay.
Thanks, Tim.